We'll proceed curl in calculus. Curl in calculus. We have done three-way switch. There is a switch comes that is three-way. So we have proved through three ways the kind of path independence in vector field. Path independence in vector field. If I have a vector field, if vector field is a simple vector, what is difference between vector field and simple vector, static vector? The difference between vector field and a static vector is there is no difference. Static vector, we have the vector has components, x component, y component, z component, orthogonal component typically. So if I have a static vector, then it has components. Static vector means components are numeric. Vector field means components are algebraic. That's it. So static vector means if I have a vector p, p on top of it arrow sign. This is a vector notation. I have a vector p equal to 2i plus 3j plus 4k. It has component 3, 2i, 3j plus 4k. 2, 3 and 4 are component which are numeric. What about capital? Now p vector is like this. Consider another vector that is x plus y plus zi plus sin x plus y plus z j plus x into y into z k. Now the three components are algebraic where all three components are available. This proves that the first component of this vector is function over x, y, z. Second component of this vector is function over x, y, z. And third component of this function is a function over independent component x, y, and z. Altogether, this is called vector field denoted by capital F. Capital F on top of it one arrow. Arrow means it is a vector. Capital F means it is a field, vector field. So vector field is a normal vector where each component is a function of x, y, z if there are three orthogonal components x-axis, y-axis and z-axis. That's it. So what are the example of vector field? Velocity vector, magnetic field, electromagnetic field, earth gravitational pull, force vector, so many, where components will be algebraic equation, not static. That is vector field. Then anyone would say, if vector field components are algebraic equation over independent component, then if I keep changing the independent component that is x, y, z, then it will generate so many static vectors. True. Altogether, I can say vector field is a function where if I keep changing the independent variable, it will keep generating one new static vector. It is a vector factory. So vector field is nothing but vector factory. How it is useful? It is useful in a way that consider consider this circle. If I denote a point, if this is x-axis and this is y-axis, then there is a point called 2 comma 3. Then what is the position vector here? 2i plus 3j. 2i plus 3j. Okay. Then it has radius as 2 square plus 3 square square root. With same radius 2 square plus 3 square root, what is this point in? Okay, consider the radius is 1 only, then there is a point called 1 by a square root of 2 comma 1 by a square root of 2. I believe it's all right. And then there is a point called 0 comma 1, there is a point called 1 comma 0. Like that there are so many points. Now for 1 by a square root of 2 comma 1 by square root of 2. The position vector is 1 by square root of 2 plus I plus 1 by square root of 2j. Here 0I plus j, 1I plus j, 1I plus 0j. If that is the case, then can I put all the position vector in some mathematical equation? Here vector field comes into the picture. So what is your circle? My circle is 1 by square root of 2I plus 1 by square root of 2j. 1 point. Next point is I plus 0j. Next point is 0 plus j. Next point is this. Now, how many points you have? Infinite. I have infinite point on my circle. Then how I can denote your circle? Okay. There are so many vectors. Then it comes as algebraic vector at the end, where it is xi plus square root of 1 square minus x square j. Keep changing the x and keep getting one position vector. This form is called vector field. If you differentiate the vector field of a circle, then you will get a tangential vector field. The velocity vector, if you have position vector, and if you get gradient of it, then you will get velocity vector that will be perpendicular to the position vector. If this is the position vector, then velocity vector will be tangent at every point. Again it will be algebraic only. That would be xi will become I plus minus x by square root of 1 minus x square, 1 square minus x square j. That is the velocity vector. That is the velocity vector, which is tangential at every moment. Let's replace x with 1, where x is 1, that is on x-axis. Then it is I plus minus 1 by 0, infinite. So j component is infinite, means along at x-axis the velocity vector is like this. Okay. So if I replace x with 0, then it becomes I plus 0j, I1. Means here on y-axis it is like this. So velocity vector is tangent, but again it is represented through algebra. If a point is represented through algebra, then it becomes algebraic equation. If a point is represented through if point vector or position vector is represented through algebra, then it becomes vector field. Okay. Now we are proceeding as curl in the vector field. What is curl in the vector field? What is curl in the? Consider that there is a vector field called x plus yi. Vector field is x plus yi. If vector field represents a force, this is what I have been talking about. If vector field represents force, if vector field represent force, if vector field represent force, then if there is a mass in the vector field, if this vector field x plus yj, then this is the vector field where it is traveling from x-axis in the parallel of x-axis. This is vector field. If I keep any item in the vector field and it get a displacement, if this is point A and it get displaced to point B, then I consider that there is a work done by the force vector field x plus yi. Since it is a force, it applied force on the mass and it got displaced from point A to point B. Then what is the work done? Work done is point A and point B. If I connect through a straight line, if I connect through a semicircular line, if this is point A and this is point B, I can connect point A and B through a semicircular line, through a straight line. Consider whatever it is, this path is, the line is also is represented as r position vector, and capital F is the vector field. Then capital F, if this line representation from A to B is a static vector and force field is also a static vector, then work done is capital F dot R vector. Capital F dot R vector. Then it is nothing but work done dot product. But if it is vector field, then it is capital F vector dot dr vector integration from A to B. This is work done by a this is work done when the vector field is force field. But if vector field is normal vector field, and if I do integration with dr, that is the line from A to B, this integration is called line integral. So line integral. If vector field is force field and r vector is displacement vector, then it becomes work done. Otherwise, the generic term for this is line integral. Now what is curling? If I have a force field that is x plus yi, this proves that along x-axis the force field is y equal to 0. Along x-axis y equal to 0. Then along x-axis the force that is in place is xi. Xi means when it is at 0, then there is no force. As you go along x-axis, force keep on increasing. Then how much is the work done from point A to point B? Point A to point B, there is a work done by this force. From point B to point A, then it is negative. The net work done from A to A, where it is A to B plus B to A to A, it is same as A to B plus B to A. Then it is 0. If the line integral from A to A, it may take intermediary path, then this is called path independent, but along all the possible path. So one path I have taken A to B, it is a straight line, then A to B, one work done, where y equal to 0, so it becomes xi. Then B to A, negative work done, so all along A to A it is 0, path independent. Now it is A to B. Now rather than directly A to B, what I would do is that from A there is another path. From A it will go from A, it will go to C. A to C. From C it will go to D. C to D. From D it will come back to B. From B to A. So integration of line integral from A to B is nothing but A to C, C to D, and D to B. Then and B to A. Again it is A to A only. Is it 0? My question. Now what is force field? Force field is I plus x plus y, I, only I. So force is completely in x-axis direction. Its strength is x plus y. Now when along x-axis A to B, when I was calculating, when then y is 0. But when there is a y, consider y is 10. At that moment this vector is x plus 10i. Then if I want work done from C to D is same length as A to B. So C to D, if I calculate work done, that is force into displacement, then force into displacement is x plus 10i. Here it is xi, there it is x plus 10i. Certainly force is more. If that is the case, then here, then C to D, this is A to B, this is C to D, this is A to C, and this is D to C, D to B. A to B, A to C, C to D, D to B, B to A. Work done from here to here, the force is xi, where C to D, the force is x plus 10i. Because y is 10, I have taken. The force equation is x plus yi. Then force is more. If I go with the same distance, work done calculation, the work done will be more. What about B? What about A to C? Then this is the path where force is perpendicular to the path. Then there is no work done. Dot product will be 0. What about D to B? Again, this is perpendicular to the force. So work done is 0. So net work done is from C to D plus B to A. C to D is more than B to A. So from A to A is A to C, C to D, D to B, B to A. If I calculate A, if I calculate A to A, then it is in a closed loop, the work done is not 0. So if I was calculating A to B and B to A, work done is 0. If I calculate C to D and D to C, work done is 0. But this is what I don't want. A to A. It may take any path. It may either it will go from A to B and B to A, or it will go A to C, C to D, D to B, B to A. Any path. Or I can have I can have A to B, then it will take circular path A to B and then B to A, or A to B and then a straight line. Any path it can take, A to A. Then it is not 0. So all possible path, the line integral in a closed loop, that is A to A, for vector field, vector field x plus yi is not 0. This proves that this is not path independent. We will talk about more in the curling. Hold on, hold on. Okay, so this is not path independent. Can I take another? So what we saw, to prove it as path independent, vector field is path independent means vector field's line integral. If it is force and line is displacement, then work done. Otherwise, vector field's line integral from point A to point B must be dependent upon point A and point B only, not on the line connecting it. Line connecting it can be circular, it can be straight line, whatever. How I can prove that my vector field is path independent? If vector field is path independent, then line integral depends upon the beginning point and end point only, not in the path it is taking. Then it is path independent. There are three proofs that we gave. First proof is that if it is path independent, let's consider any generic path. From A to B, let's consider any generic path. Either it is a circle, it is a straight line, it is parabole. Then any point on the path can have coordinate x comma y. That is generic point. If that is the case, then position vector of x comma y is xi plus yj. If vector field capital F will have components f1i plus f2j, capital F, then the line integral is capital F dot dr vector. R vector is xi plus yj. Dr will become dxi plus dyj. Dxi plus dyj. Whereas capital F vector field becomes f1i plus f2j. If I do dot product, it becomes f1 dx plus f2 dy. f1 dx plus f2 dy. If that is the case, f1 dx plus f2y is the f1 dx plus f2 dy. This integration will lead to a potential function or algebraic equation. f1 is algebraic, dx integration will be algebraic, plus f2 is algebraic, then dy integration will be algebraic. Algebraic plus algebraic will lead to algebraic equation at the end. Limit a to b. Now this algebraic equation, if this algebraic equation f1 dx, capital F, f1 dx plus f2 dy result in algebraic equation that is denoted by small f, that is potential function. Then if I go with reverse, then small f potential function or fxy, dfxy by dx will be f1 and dfxy by dy will be f2. Okay, so when we are going for a generic equation, then f1 dx or f1 equal to dfxy by dx. If f1 dx equal to algebraic function fxy, I mean f1 dx plus f2 dy equal to algebraic function fxy. Or in reverse term, this terminology, if it is going with fxy, then if I go reverse way, then its gradient vector is f1i plus f2j. Then only it is possible. If that is the case, then dfxy by dx, small f, dfxy by dx, I plus dfxy by dy, j is nothing but capital F, f1i plus f2j. If that is the case, then dfxy by dx equal to f1. Then dfxy equal to capital F1 dx. But we said f1 dx plus f2 dy equal to fxy. But as per the calculus, dfxy by dx is f1. This proved that fxy equal to f1 dx, f1 dx, whatever comes plus some constant. That constant is function over y. Then only dfxy by dx equal to, if fxy equal to capital F1 dx, capital F1 dx, then if I calculate capital F1 dx plus any function of y, then dfxy by dx will become F1 plus plus nothing. Means it looks little cumbersome. This is how the multivariable calculus is. Then we will go along and we will differentiate dfxy with dy, and then we settle it down to find out the f2. This is the way. But with generic line from point A to point, that is xi plus yj, we found that if line is generic, then it is the whole line integral is f1 dx plus f2 dy. If this results into a potential function small fxy, then fxy by dx is f1, dfxy by dy is f2, capital F2. If that is the case, then fxy equal to df f1, capital F1 dx plus any function of y. Then if I do partial derivative with dx, then f1 dx becomes f1 plus nothing. Whatever comes, we will settle it down. So this is the one way we try to prove that it is path independent. Path independent means if I say f1 dx plus f2 dy is my net potential function because it is path independent. If that is the case, f1 dx plus f2 dy is my fxy, then as per algebra, then dfxy by dx will be f1 and dfxy by dy will be f2 as per the algebra, as per the calculus. If that is the case, then dfxy by dx is f1, but it is partial differentiation along x-axis. Dfxy by dy partial differentiation along y-axis, small f. Then it is a gradient vector that is equal to f1i plus f2j, that is f1, that is f vector. Means if I go through generic way and then if I find a potential function small f for which gradient vector is vector field, then it is path independent. This is, we started from the xi plus yj, but other way also we can do. Two way I showed that if it is, that is our proof. If I search any potential function in the world, small f, any potential function in the world, small f, for which gradient vector is the vector field, then vector field is path independent. Because fxy is small f, if a small f is algebraic function and we are talking about line integral from point A to point B, then small f b function over b, point B, small f b minus f a, small f b minus f a equal to integration from A to B gradient of f, small f dot dr vector. If this is the normal calculus fundamental that we saw, f integration from A to B gradient of f, small f dot dr vector is equal to small f b minus small f a. This is normal calculus. But if this is the scenario, then fb minus fa is only dependent upon gradient of f, not on the r vector. Then it is line independent. But in our equation, we have A to B capital F dot dr vector. So if capital F is equal to gradient of a small f potential function, algebraic function, that is the result, then it is line independent. Through all the permutation combination, we proved it. But the way we proved it, we will go with that way only. That is that I took a generic path from A to B, that is xi plus yj, and then integrate, then dr vector becomes dxi plus dyj, and capital F vector is f1i plus f2j, dot product becomes f1 dx plus f2 dy, and then this integration comes to as small f. If that is true, then as per calculus, small f by dx is f1, small f by dy is f2. Okay. Now, can we prove that y cos x I plus sin x plus yj is a vector field? Y cos x I plus sin x plus yj is a vector field. It is path independent or not? Okay, if this is the vector field, then potential function will be f1 dx plus any function of y. Then f1 is y cos x. So if I do dx, it becomes y sin x. So fxy, small f, potential function, end result, small fxy equal to y sin x plus cy, any function over y. If I do partial derivative along x-axis, dfxy by dx, then y sin x become y cos x plus gone. This is what is f1. So, alright. Now, fxy we got, that is y sin x plus any function over y, cy. Now, if I do dfxy by dy, then y sin x becomes sin x plus derivative of function cy. But dfxy by dy is f2 as per our fundamental, where f2 is sin x plus y. So sin x plus y equal to sin x plus derivative of any function cy. Sin x gone, derivative of any function cy equal to y. Then cy equal to y square by 2, and as per our principle, cy has to be a function of y only. So y square by 2, alright. So if that is the case, then then we have now f1 and f2. Then we have now the fxy. So fxy is nothing but f1 dx plus any function cy. So f1 dx is y cos x. F1 dx is y cos x. So I'm sorry, it was y cos x, so it is y sin x plus cy is y square by 2. So the end result, that is potential function, is y sin x plus y square by 2. Let's do partial derivative with x and y sin x plus y square by 2 dfxy by dx, then it will come as y cos x, that is capital F1, dfxy by dy, then it will dy. So if it is y sin x plus y square by 2, that is fxy, then dfxy by dx is y cos x, that is capital F1. dfxy by dy is sin x plus y, that is F2. Pretty clear, pretty clean. So capital F1, then field vector, the vector field capital F is path independent. If it is path independent, then circular line integral from point A to A. If I have a vector field with equation is y plus cos x, y cos x I vector plus sin x plus yj, then this vector field is line independent, path independent. In that way, if I have along x-axis, if I have 2 points A and B, and against this vector field, if I calculate line integral, then from A to A, means A to B plus B to A, it will be 0. Or if I take a rectangular region, A to C, C to D, D to B, B to A, that is A to A only, again it will be 0. All path, because it is path independent. If I take a semicircular region from point A to B, then A to full semicircle to B and B to A back through a straight line, again it will be 0. No need to calculate for all possible paths. It is path independent proof. This is how mathematics is. Okay. Now, what is importance of path independence? So that how it leads to fundamental of curling. Now time has come that we will talk about curling. What is curling? Curling is that if this is a vector field and against this vector field I place an item, if this is considered this is vector field like river is going, vector field not, it can be along the x-axis only, it can be along x and y-axis. I'm not stopping it. Even if it is along x-axis, then it is not guaranteed that if I place an item will move like this. Item may rotate. Can you believe it? If river looks like it is flowing in one direction, if a person is going inside the river, expectation is he will flow along the river, but not required. He may start rotating. Can you believe it? If someone is going inside a river, there is some chance. God's sake, it should not rotate. But practical sense, empirical way, it never sees the God sense. Okay, whatever is truth, mathematical truth, it will happen that way only. So if a person is entering into river, consider river is flowing from left to right, and if you go in deep, then he starts circulating. Amazingly, so if I have a vector field along y-axis and along x-axis, if I place an item, considering item will go as per the vector field but not guaranteed. It may rotate. What is the tendency of this vector field to make any item rotate? That is called curling. So now path independence, all possible way, we have done all the investigation. All three way we have done the investigation. Please watch last two videos. Then you will understand. Then now it has time that we will prove the kind of how a vector field can produce, how a vector field is path independent or not, we prove it. But if it will produce curling, that we will see. It is associated with path dependence and path independence. Okay, so meanwhile, we are accepting support from people, and if you are capable, if you are getting benefited through our calculus tutorial, then if you are benefited and if you are capable, then please support us. Okay, our telephone number is +91, that is India, 9483160610. 9483160610. Okay, so please support us.